Next speaker, we are having Jesang Yim, so you can share your screen and then we can begin. So our next student speaker will be Jesang Yim. Will be giving a presentation on estimation of post-Malin particle size distribution using linear transformation in parameter space. Jesang, are you here with us?
Yep.
Okay,
is my screen shared?
Yeah. Okay, we saw it. So just begin when you are.
Okay. Hello, my name is Jesang Yim, and I will talk about my research on estimation of post-Malin particle size distribution using linear transformation in parameter space. This research is basically about predicting the post-Malin particle size distribution using the pre-Malin particle size distribution. As a student living in a very rural place in New Hampshire, I was always interested in farming and agricultural lives here. Wondering about the particle sizes of the farm products and the way they are milled, I found myself interested in milling process of particles, not only agricultural products, but also metal particles. By then, I found this topic in InnoCentive website. InnoCentive is a website for problem seekers and solvers. Problem seekers can be companies, industrial organizations, or individuals who want to solve any kind of problems in their business. Problem seekers can ask for help anonymously, and it is impossible to figure out who asked which questions for what reasons. After getting the idea and data from InnoCentive, I started to think about why solving these questions is so important. In milling industry, companies require some sort of standard sizes, and they want the milled particles to be somewhat accurate. However, currently in milling industry, all the particles that are not milled into certain sizes are all being wasted. To reduce the amount of waste, predicting the size distribution before milling is very important for them. Since the website kept the problem seekers as a secret, the research was all mathematical studies. So I started to dive into the research. In order to do this research, I had to make two assumptions. First of all, I assumed that graphs that do not look like normal distribution graphs are composed of several different normal distribution graphs. Next, I thought there must be some kind of linear formula that can be used to predict the post-milling size distribution. Apparently, the hypothesis of this research is that the distribution of particle sizes in post-milling data can be predicted using normal distribution functions of particle sizes of pre-milling data, and finally find the formula, the transformation matrix. This research is not only applicable to particle milling size distributions, but also in predicting post-event distribution data using the pre-event distribution data. Next, I'll talk about my background research. Milling is a process of turning bigger particles into smaller particles. In this research, slurry milling was used to grind the metal particles, and slurry milling is a process of milling particles with certain kinds of liquids. The prediction of size distribution of particle milling was not researched previously. Normal distribution is a function that shows the probability of variables. Normal distribution graph shows the amplitude, mean, and standard deviation of the function. As you can see here, normal distribution function can be written as expression on this slide. A, B, and C are all called parameters, and it will be used later in finding the matrix. For this research, computer language program was needed. In this research, Mathematica was used. As mentioned earlier, all the data was provided from the problem seeker in InnoCentive. This research is divided into three different procedures. Firstly, deciding the number of normal distributions to describe the particle size distribution. Secondly, determining the transformation matrix using the parameters from the number of normal distribution functions. And lastly, calculating error and measuring the performance of found prediction. In deciding the number of normal distributions, I tried 2, 3, 4, 5, and 6 normal distribution graphs to compose the pre- and post-milling size distribution graph. From this process, just using 2 normal distribution graphs had the worst result with error of about 58%, and 5 normal distributions came out to be the best case as shown in the graphs on the slide. Although 5 normal distribution graphs showed the best result, since the size and the number of data given by the problem seeker in incentive was not enough to test the result after finding the result, I could only use 4 normal distribution graphs to form the non-normal distribution graph. Parameters from the normal distribution functions were used. Since there were 4 normal distribution functions, there were 12 parameters in total. Using these parameters, I was able to find the transformation matrix size of 12 by 12. After finding out the transformation matrix, I was able to actually use it and test it for every data set. 2 trials were done. First, I tried with 3 normal distribution graphs, and second, I tried with 4 normal distribution graphs. And as you can see here, only using 3 normal distribution function fits poorly, and using 4 normal distribution functions fits pretty well. As the diagram shows here, multiplying the pre-milling size distribution parameters to the key matrix gives the post-milling size distribution parameters. 12 by 12 matrix is multiplied with 12 by 1 matrix, giving off 12 by 1 matrix. Using 4 normal distribution functions had the average error of 1.49%, which was pretty low compared to other number of normal distribution graphs. Although using 5 normal distribution function had the least error, since the data was limited, it was not able to create the key matrix consist of parameters from 5 normal distribution functions. Therefore, it was possible to predict the post-milling particle size distribution using the formula matrix and pre-milling particle size distribution. In the future, I would like to carry on 2 different kinds of future research. First of all, if possible, I would like to continue this research with more data. I would like to test the errors and accuracy of 6, 7, or even 8 normal distribution functions. Theoretically, it came out that the research had higher accuracy and precision result when using greater number of normal distribution functions, but I would like to try if it overfits and give worse result. Next, I'd like to use similar techniques and mathematical methods on different events that needs the prediction of after result distribution data using the before event distribution data. Also, since I am very interested in milling process itself, I'd like to continue the research on milling machines and its mechanical analysis. Here's my citation for the work, and thank you for listening.
Thank you, Jesang. So now we're going to open up for Q&A. So leave your question into the chat or in the question functions. Great. So we got a question. So upon completing the project, do you get to meet the person who requested your help?
Good question. As I mentioned earlier, since Innocentive kept it secret who asked for the question, I could not know which company was asking for the problem and like why they are asking for this question. I just took the idea from the website.
Awesome. So I believe that is all, and that is wrap up today for block 1 for this term. So thank you so much, everyone, for joining and listening, and also to all of our student speaker for presenting your amazing research. Thank you so much, everyone. Take care.